Good morning, Calculus. Happy surprise e-learning day. We are going to be watching this video on Intro to Antiderivatives and Evaluating Integrals, but what I want you to do first is attempt to fill out this table yourself. So I want you to pause the video right now, attempt to fill out this table yourself. What you're asking yourself is, what function would I differentiate to get sine? What function would I differentiate to get 2x? So if I took the derivative, 2x would be my answer. If I took the derivative, sine x would be my answer. For the first one, I'm guessing you wrote down some version of cosine, which is perfect. But if I take the derivative of cosine, I would get negative sine. So the antiderivative of sine would have to have a negative in front of the cosine. For 2x, hopefully you wrote down x squared. If you took the derivative of x squared, you would get 2x. I'll show you a way to figure those out all of the time later at the bottom, but hopefully that one you could get on your own. 5, in order for 5 to be a derivative, it would have had to have an x next to it, because the derivative of 5x is just 5, the coefficient on the x term. Okay, this one's a little tricky. This is like 1/4 x. So you know when the exponent comes down, when you differentiate, it has to multiply to get 1/4. So I know the exponent needs to go up. This is a linear function, so its antiderivative would have to be quadratic. So I'm like, okay, I'm going to make this an x squared. The only way that this would become a 1/4 is if it started as a 1/8, right? Because then 2 times 1/8 would be 1/4. Okay, this one is 1 over x, the antiderivative. What function do we differentiate to get 1 over x? That's natural log. But right now I want you to put absolute value bars around the x, and we'll discuss that later. E to the x, that one should be easy. We know that the antiderivative of e to the x is e to the x because the derivative of e to the x is e to the x. Antiderivative of secant squared, what function do I differentiate to get secant squared? That would be tangent. And then the last one, hopefully you recognize as one of those crazy formulas for inverse trig derivatives. This was inverse tangent. Okay, now, there's one thing missing on all of these. If I were to take the derivative, I'm just going to use this one. If I were to have asked you at the beginning of the year to take the derivative of x squared plus 3, you would have told me that derivative is 2x. If I ask you to take the derivative of x squared minus 1, you would also tell me that's 2x. So for that reason, we need what's called a constant of integration. So constant of integration is representing any constant that if you took the derivative of it, it would be 0. Okay, because we're coming up with a general form or general solution for an antiderivative. So we need to make sure that we include the plus c on all of these. Okay, these are called antiderivatives for indefinite integrals, which we'll talk about down here. So essentially, if dy dx equals f prime, then y is the original function plus c, the constant of integration. Okay, what you see below are all indefinite integrals. Indefinite integrals, you'll notice in the past few days we have been doing integrals with bounds on them, a lower bound and an upper bound. Indefinite integrals do not have bounds on them. So you are just coming up with a general solution that produces the derivative that you see inside the integral. For example, 3x squared. Hopefully we know, just using mental calculus math, that x to the third would produce the derivative 3x squared. We include the plus c on it because that is our constant of integration. An easier way, if you're like, how is Mrs. Nodelman doing this without actually figuring it out? When you think about taking a derivative, if I ask you to take the derivative of x to the third, you multiply by 3 and subtract 1 from the exponent. For antiderivatives, you do exactly the opposite. You add 1 to the exponent, so this would become 3x to the third, and you divide by the new exponent. So the new exponent is 3. I divide by 3, and that's where x third comes from. For x to the negative second, you do the opposite of multiply and subtract, which is add and divide. So you add 1 to the exponent, that would become x to the negative 1, and then you divide by negative 1. To simplify this, I would make it negative x to the negative 1 plus c, or even better, negative 1 over x plus c. Cosine. People get the sign, S-I-G-N, incorrect with cosine and sine all the time. So what I like to do is just say, okay, if you see cosine, let's write down sine. We know that it's a version of sine plus c, and then take a derivative and just make sure that the derivative of this gives you cosine. So the derivative of sine x is positive cosine x, so we're okay. The next one is a square root of x, so I'm going to rewrite that as x to the 1/2, just like I would if I was finding a derivative. And then I add 1 to the exponent, so x to the 3/2, and you divide by the new exponent. If you divide by 3 over 2, that actually becomes a 2/3 in front. The next one, x to the 6th, I add 1, x to the 7th, divide by the new exponent over 7 plus c. You could even make it 1/7 x to the 7th, same thing. Last one, I see cosecant squared, so I know that it has to have something to do with cotangent. I double check. The derivative of positive cotangent is negative cosecant squared, so that works. I'm guessing you're seeing how important it is that you memorized your derivatives. If you need a refresh on your derivatives, there's one linked on our Canvas pages. Okay, so now that we know how to find antiderivatives, we should be able to evaluate a definite integral. So you'll notice again that these did not have bounds on them, so we were coming up with general solutions that would produce the derivatives that we see inside the integral symbol. Here we're evaluating definite integrals. Evaluating definite integrals involves the second part of the fundamental theorem. We will learn the first part of the fundamental theorem of calculus later. So this is part 2 of the fundamental theorem, which tells us that if you want to evaluate the area between the curve and the x-axis, you can evaluate the antiderivative of the function at the upper bound and subtract the antiderivative of the function at the lower bound. Okay, so you're going to find the antiderivative, sub in the upper bound, subtract, sub in the lower bound. So for this first one, I have to find the antiderivative of 2x minus 5 first. Again, the antiderivative of 2x, you would add 1 to the exponent, so 2x squared, and divide by 2. Okay, if you can see that as just being x squared right away, that's even better. Minus 5x from negative 2 to 6. I'm going to sub in the upper bound first, subtract and sub in the lower bound. This is the notation that we use. This is a bar that's showing us, okay, I'm about to substitute now. So I end up getting 6 squared minus 5 times 6. Okay, that's our upper bound, minus negative 2 squared minus 5 times negative 2. So 36 minus 30, 4 plus 10. So 6 minus 14 is negative 8. Okay, that is the fundamental theorem. So we're taking the upper bound, subbing it into the antiderivative, minus the lower bound, subbing it into the antiderivative. Same thing here. The antiderivative of 7 is 7x. From root 2 to 10 root 2. So we get 70 root 2 minus 7 root 2. Because those have the same radical, you can subtract and get 63 root 2. Antiderivative of sine. Again, if I'm not sure, I write some version of cosine down. The derivative of cosine would give me negative sine. So to get a positive in here, I'm going to make it a negative cosine. From pi to 2 pi. So I'm going to do negative cosine of 2 pi minus negative cosine of pi. This turns into a positive. So negative cosine of 2 pi. On the unit circle, cosine of 2 pi is 1. So this is negative 1 plus another negative 1. Cosine of pi is also negative 1. So negative 2. Letter D, this is x to the negative 2, so I can add 1 to the exponent. I get x to the negative first and divide by negative 1. So we end up just getting x to the negative first, or it's easier to write that as 1 over x, especially when we're about to evaluate it. So 1/4 minus 1 over 1 is negative 3/4. Okay, keep in mind you're only doing this once. So there's a lot of times where students will find this antiderivative, they'll get 1 over x, and then their answer will magically turn into natural log. 1 over x is only producing an antiderivative of natural log if you started with it in the integral symbol. So just do 1 antiderivative, sub in the top bound, minus sub in the bottom bound. Okay, secant squared. Antiderivative of secant squared is tangent from negative pi over 4 to pi over 4. So I sub in pi over 4, subtract, and sub in negative pi over 4. Tangent of pi over 4 is over here in quadrant 1. Remember, this is pi over 4, root 2 over 2, comma, root 2 over 2. So if you put root 2 over 2 on top of root 2 over 2 as a fraction, you end up getting 1 minus. Tangent of negative pi over 4 is down here. So again, we have positive root 2 over 2 and negative root 2 over 2. So minus negative 1. We end up getting an answer of 2. Okay, e, antiderivative of e is still just e from negative 1 to 5. So e to the 5th minus e to the negative first. You cannot combine those, so the best you can do is just write it as e to the 5th minus 1 over e. All right, from a table, there are a few like this on the AP Classroom assignment. So when you're looking at these integrals, the first thing you want to do is ask yourself, can I easily find the antiderivative of the function they're asking me about? So if f prime is inside an integral symbol, if you're working backwards, what function do I find the derivative of to get f prime? Hopefully you're like, that seems like a difficult way to ask an easy question. It's just f of x from 1 to 3. Right? F of x's derivative is f prime. So that's f of 3 minus f of 1. F of 3 is 0. F of 1 is negative 1. So I end up getting 1. Right? F of 3 is 0. F of 1 is negative 1. Okay, now this one is a little bit trickier. Hopefully you're looking at that thinking, how are we supposed to do products with antiderivatives? And you are correct. But my goal for you, Ms. Gilbert's goal for you, is to notice that that is actually the result of chain rule, right? Derivative of the outer function, the inner function is g of x times the derivative of the inner function. So chain rule starts out as f of g of x from 1 to 3. So that's f of g of 3 minus f of g of 1, right? The derivative of f of g of x becomes that. Okay, so g of 3 is 2, so we need f of 2. G of 1 is 0, and we need f of 0. So then f of 2 is negative 7, and f of 0 is 4, so negative 11. Okay, again, hopefully this video helps you start your AP Classroom assignment. We will do some cleaning up of all content tomorrow in class as well. Have a good day.